Okay, so here we are on the last topic in this course. In the last class we had talked about auto-epistemic logic, and that was a logic in which we had added a belief operator which talked about the beliefs of the agent essentially. So, you could say that the agent believes in something and so on and so forth. Today we want to extend that idea and we want to move from the notion of belief to a notion of knowledge. About 50 odd years ago, Hintika had written a book called Knowledge and Belief, which was in those days considered to be a book on philosophy, but it was very instrumental in giving impetus to reasoning about knowledge and reasoning devising logics for reasoning about knowledge and things like that essentially. So, this what we are saying is an offshoot of that essentially. So, the references for these books are different from what we have done for the course so far. So, the primary reference is this book called Reasoning About Knowledge by Fagin, Halpern, Moses and Vardy, but there are other references here, especially to something called dynamic epistemic logic, which we will not consider too much, but we will at least allude to in the class essentially. So, there are these two sources by Hans van Ditmars, and there is one Stanford Encyclopedia of Philosophy, which is a kind of a Wikipedia, not Wikipedia, it is basically an encyclopedia essentially. Okay. So, let us begin with this thing. We start with a puzzle. This has been adapted from this website that you can see here. So, there is Cheryl says to Albert and Bernard that I have given you two different numbers. Can you guess which is the larger number? So, there is a sequence of responses. Albert says I do not know, Bernard says I do not know, Albert says I still do not know, and then suddenly Bernard says that now I know which number, which of us has a larger number. Then Albert says that in that case I know both our numbers essentially, and then finally Bernard says I also know both the numbers. So, I am sure you must have encountered puzzles like this, which essentially deal with what the different people know about each other's knowledge essentially. So, the question is what are the numbers that we have to answer is what are the numbers Albert and Bernard have essentially. So, I will give you another puzzle to solve for yourself. Let us look at this answer right now. So, let A be Albert's number and B be Bernard's number, and remember they both know their own number, they do not know the other person's number essentially. And then Cheryl says that I am giving you two different numbers starting with 0, the lowest is 0, natural numbers you might say, and you have to tell me who has a larger number essentially. So, first Albert says I do not know, and as you can see this implies that his number cannot be 0, because if his number was 0 he would have known that he has a smaller number. Remember that the two numbers are different essentially, and once Albert says I do not know, Bernard knows that Albert's number is not 0 essentially. Then Bernard says I do not know either, which means that his number, which is B, must be at least 2 essentially, if not more than 2, because if it was 0 or 1 then Bernard would have known that Albert has a larger number, and Albert does not know who has a larger number essentially. Albert says even though you say that I still do not know. Now, this if you go through this process of reasoning you will see that it implies that his number is at least 3 essentially. If at that point Bernard says I know which of them has which of us has a larger number, and this implies that B must be either 2 or 3, and also that Albert has a larger number essentially. After that is Albert says I know both the numbers essentially. It basically means that A must be 3 and B must be 2, and therefore Albert could figure out that that he has that Bernard has 2 essentially. And at that point Bernard also figures out that Albert has 3. So, at the end of this conversation both of them know what the two numbers are essentially, and so the answer is Albert has 3 and Bernard has 2. So, I will give you a small puzzle for an exercise, you can do it later, do not try to do it now, and here is a puzzle. So, the year is 1968, maybe you were not born then, but still you are sitting with two bridge world champions and then in walks your tormentor goat bully, and he says that I have 3 caps from a collection of red and black caps, and he holds aloft a box out of which one red cap falls down. So, you know that of the 3 caps that he is bringing, one of them is at least red essentially. Then he blindfolds you and all 3 of you, and he puts the 3 caps on your head, and then he asks you repeatedly, do you know the color of your cap essentially. So, it turns out that first he asks Gallozo, and Gallozo or Benito Gallozo says no. Then he asks Belladonna, Giorgio Belladonna, he also says no. Now he is coming towards you, and it is your turn now. What will you say essentially? So, this is a small exercise that you must do sometime offline essentially. These are the kind of puzzles that this is the kind of reasoning that we do when we talk about reasoning about knowledge in a multi-agent scenario. So, who knows what, and what do you know about what the other person knows, and so on and so forth essentially. So, we use this term epistemic logic for that. Epistemology is basically the science of knowing, or the art of knowing, or whatever, reasoning about knowledge, primarily used in situations involving groups of agents essentially. It has found large applications in reasoning about distributed systems, for example. The kind of questions we ask are, what does a given agent know about the world? So, we are also operating in an incomplete environment essentially. We are not assuming that everything is known to an agent essentially. And then higher order reasoning as to what does a given agent know about what other agents know. These are the kind of questions we want to ask. So, you saw those 2 puzzles that we saw, they are reasoning about why are they answering like this, because that we are saying that they must be knowing something, and we are trying to figure out this whole process. So, first, we are talking about a propositional epistemic language here. So, first let us just deal with the syntax. It is very simple, that a sentence in this language is either an atomic proposition, which is basically from the simple propositional language, any statement P. Otherwise, if omega is a sentence, then, or if phi is a sentence, then negation of phi is a sentence, or phi and phi is a sentence. Now, remember we had discussed towards the beginning of the course that if you have negation and it is a complete set of binary connectives, which means you do not have to specify other connectives, implication or all of them can be expressed in terms of negation and. So, for our purposes we will assume that as and when required we will be able to express those things in this language essentially. And the new thing is this modal operator K. It has a subscript A which stands for an agent, because we are talking about a multi-agent scenario now, and the formula K A phi reads that agent knows the formula phi essentially. This is a new thing in epistemic logic, which is not there in propositional logic. So, this unary epistemic operator K is similar to the belief operator that we had discussed, and you can even talk about belief operators in a multi-agent scenario. So, instead of just saying B, you can say B of A, what agent A is belief. The main difference between belief and knowledge here is that the knowledge operator is applicable only to true sentences essentially, whereas belief operator may be applied to sentences which are not true. So, you may believe that the earth is flat, but you cannot say that you know that the earth is flat. So, that is the difference between these 2 operators, and that is characterized by one of these axioms of epistemic logic, which is called axiom T, which is also called the truth axiom, which says that if an agent A knows something, that thing must be true essentially. This is one of the axioms with epistemic language, and like many logics, people have tried different kinds of epistemic languages with different kinds of sets of axioms. So, I have just listed here some axioms here. These I have taken from the Stanford Encyclopedia of Philosophy. The first knowledge axiom is the most common, which is basically the knowledge axiom. If you look at it closely, you can see that what it says is that if an agent C in this case knows that A implies A prime, and so if an agent knows that A implies A prime, agent C knows that A implies A prime, then if he knows A, then he knows A prime essentially. So, if you sort out this formula, you know that P implies Q implies R is equivalent to P and Q implies R, which is basically the form of modus ponens that we had studied. So, in this case you can actually club these together with an and put a clause here and say that if he knows that A implies A prime and if he knows A, then he knows A prime essentially. So, that is the basic knowledge operator, that the agent is able to reason with what the agent knows essentially. This D is talking about possibility, we will talk about it a bit later. It basically is saying that if agent C knows A, then agent C considers A to be possible, and we will see why that is the case a little bit later essentially. The third axiom T is what we discussed a little while ago, it is called the truth or veridicality axiom. It basically says that you can only know true things essentially. The fourth and the fifth are, we are familiar with that they are the positive and negative introspection. It says that if you know A, then you know that you know A, and if you do not know A, then you know that you do not know A essentially. So, positive and negative introspection, which is part of the auto-epistemic logic that we had discussed earlier also, and there are a couple of more axioms that we can think about. So, people have described various devised various languages. The simplest of them is simply has system K, which only uses the first thing, but most of the time the language that people have preferred is called the system T, which uses the truth axiom as well as the knowledge axiom. The system that we are kind of going to talk about is system S, which also uses the positive and negative introspection. So, you can see that in some sense it is a carry forward from the belief operators we saw in the last class, except that we are talking about knowledge here, which is different from belief in the sense that you can only know true things. So, that was the syntax of the language. Yes.
What were the numbers 5, 1, 2, 3 and
so, there are those as I said, there are other axioms and you can add those axioms and you can get languages like S5 and S4.2 and S4.3 and all, but we do not have time to discuss those here. Those are slightly languages which have stronger axioms with that. So, let us talk about the semantics, that how can we talk about semantics in this epistemic logic. The answer that is now most popular is given by Saul Kripke, who was born in 1940, and he defined as semantics of epistemic logics, and remember that they are working in an incomplete, all working with incomplete knowledge. So, this Kripke semantics as it is now called is introduces the notion of possible worlds essentially. So, every agent can imagine many possible worlds. So, as we will see, sometimes the agent is able to assert that a certain formula is true, but sometimes the agent has confusion about whether a certain formula is true or not. So, we will come to that later essentially, and such models are now known as Kripke structures, and we will have a quick look at them today. So, in different possible worlds, different sets of propositions would be true, but the agents are not able to distinguish between certain propositions whether they are true or false, and so we will look at some of those notions. Even though in the real world or in reality there is only one world in which you know what is true or not, but the agents, because of their incomplete knowledge, imagine many possible worlds essentially. An example that we will see shortly is, for example, if I give you the statement it is raining in Delhi. Now is this statement true or is this statement false essentially? With the limited knowledge that you have got sort of locked up in this classroom, there is hardly any way of knowing whether it is raining or not. So, you can imagine two worlds, at least two possible worlds. In one possible world it is raining in Delhi, and in another possible world it is not raining in Delhi. So, you are not able to answer whether that sentence is true or not essentially. So, we will look at some of these issues. Okay, so what I am doing now is from this book. So, let us define Kripke structures. So, let S be a set of states or possible worlds. Let phi be a set of atomic propositions that we are interested in. Let pi be a interpretation or a mapping which for every possible world maps every proposition to either true or false essentially. So, it is an interpretation, except that this interpretation will also take the state as an argument and say in this state this statement is true. So, you know, if you look at the Kripke structure, you can say that in state S1 certain form statement is true, in state S2 that particular statement is false and so on. So, this function pi or interpretation tells us that let A be a set of agents, and for each agent in this set we define a binary relation, which is for agent A we will call R A, which is on the cross product of the set of states S cross S. So, it basically links states together, and the binary relation links those states together which the agent cannot distinguish between essentially. So, you cannot say whether you are whether it is state S1 or whether it is state S2 if that S1 S2 happens to belong to your binary relation essentially. So, again we will see examples and that should make it clear essentially, but basically this relation will tell you how to model the confusion or lack of knowledge that a particular agent has essentially. So, the Kripke structure is basically a tuple where you have the set of states, you have the interpretation function, and you have this relation, and you can model it as a set of relations where one for each agent R1 up to Rn essentially. Okay, so, given a state or given a world or possible world, how can we say whether a formula is true or not essentially. So, we define the notion of entailment. So, M is a Kripke structure and S is a state. So, you are asking whether given this Kripke structure and given this state S in the Kripke structure whether a formula is true or not essentially. So, if the formula is a proposition, then it is simply true if the interpretation tells you that it is true essentially. So, if pi the function pi tells you that in state S proposition P is true, then it is true essentially. Then the AND is dealt very similarly as we do in any other logic, that if both of them are independently shown to be true, then they are true. Negation is likewise treated as in any other language, that if you cannot show it to be true, the negation of that is true. What is important or what is interesting from or new from our point of view is how do you show that a formula like k I phi is true essentially. So, when can you say that an agent knows a formula phi essentially? We say that it is true if that formula is true in all the worlds which are connected to S as far as the agent is concerned. So, it was so the form. So, when we are asking about k I phi, so it is a modal operator. You are saying that if you can show phi to be true in all worlds T such that ST belongs to the relation for that agent essentially. In other words, in all the worlds that the agent cannot distinguish between, if that formula is true, then the agent knows that formula to be true essentially. So, let us take a small 2 agent example, this example that I had just mentioned to you. The Kripke structure is there are 3 states in this example S, T and U. There are 2 agents, agent 1 and agent 2. Each of them has a relation R1 and R2, which we will show graphically. I will not write it here. There is only one statement that we are interested in at this moment, which is that whether it is raining to be true, and it so happens as described here that it is true for states U and S, the statement P is true, and for state T the statement P is false. So, now what is the relation R1 and R2? We depict this graphically. So, every edge is a relation. So, you can see that the relation is a reflexive relation. So, for every state S, T and U, there are arrows going labeled with the agent name. So, this diagram shows that the edge label tells you as to for which agent we are talking about this relation essentially. So, if you look at this diagram now, you can see that agent 1 cannot distinguish between states T and S essentially, whereas agent 2 cannot distinguish between states S and U. This is just a Kripke model given to us essentially. So, what does it mean? Supposing P is a statement, it is raining in Delhi, and let us say we are in state S and we are asking, is this statement true in state S essentially. Then of course, we have to simply check whether it is true in S or not. But if we say, does the agent 1 know in state S that it P is true, then we have to do this analysis, which we will do in a moment essentially, and likewise for agent 2 essentially. So, one question you might ask is, are the states S and U same or different? I mean, they look same because they have only one proposition, but you can imagine that there were other propositions around essentially. One S could be, for example, if you are in Delhi itself, then you know of course it is raining in Delhi or not raining in Delhi. U could be a state where you have a television on where weather reports are playing and things like that. But so you can imagine all sorts of situations. As far as we are concerned, there are these 3 states. Agent 1 cannot distinguish between T and S, and agent 2 cannot distinguish between S and U essentially. And in S and U, P is true, and in the state T, P is false essentially. So, now again notice that we are asking the question with respect to state S. In the state S, we are saying that agent 1 does not know P. Why is that? Because you can see that for an agent to know P, P must be true, or for any agent to consider P true, P must be true in all the related sets essentially. And you can see here that in this set, T and P, so it's true in S, but it's not true in T. So, we cannot say that agent S knows P, because even though we are talking about agent 1, even though we are talking about state S, but we have already stated that agent 1 cannot distinguish between state S and state T. So, agent 1 cannot say whether P is true or not true, but agent 2, as you can see in this example, can say that P is true, because agent in both the states that agent 2 cannot distinguish between, that is S and U, in both those states P is true. So, agent 2 can say that P is true essentially. The third formula says that agent 1 knows that agent 2 knows P, or agent 2 knows not P essentially. So, in other words, agent 1 knows that agent 2 knows whether it is raining or not in Delhi essentially. Why is this formula true? So, again if you remember, the way that this works is a formula which has a k operator will be true if, and this is for with respect to agent 1. So, it must be true in all the states that one cannot distinguish between, which is the states S and T, as you can see here. In state S, this formula is true because in state S agent 2 knows P, we already have seen that. In state T, the only other state reachable for agent 2 is state T itself, there is only the self loop and nothing else. So, and in the and state T not P is true. So, this formula is true. So, because it is a disjunction, both formulas are true, and therefore, agent 1 knows that agent 2 knows whether it is raining in Delhi or not essentially. So, we are simply talking about the truth value of statements. We are not really talking today about how to derive whether this formula is true or not. We are talking only about entailment, not of derivation. This last one I will leave it as a small exercise for you to say that agent 2 does not know that agent 1 does not know that it is P essentially. Essentially, you have to basically recursively apply the way for evaluating a sentence with a knowledge operator essentially, and the negation in this case. So, let us look at a couple of more examples. So, these are kind of very common in this community, and there is a tiny pack of cards, really tiny. So, let us say there are 3 players, Anne, Bobby and Bob and Kathy, and we will call them A, B and C, and there is a small pack of cards with 3 cards named 1, 2 and 3, and let the set of statements be of the kind that player P holds card some player holds a particular card. So, 2 subscript B for example says that Bob, which is B, holds the card number 2 essentially. So, we have statements like this, and here are some common sentences and their intended meanings. This sentence simply says that A is Annie, remember, knows that Bob holds 2 essentially. So, we are not saying whether this is true or not, because we have not described any world here, but what are the sentences and what they intend to mean essentially. The second sentence says that Annie knows her card essentially, because either Annie knows that she is holding 0, or she knows that she is holding 1, or she knows that she is holding 2. So, she must be holding one of them. So, she knows.
The issue is your cards named as 1, 2 and 3 and you have 0, 1 and 2.
Yeah, okay, I can solve that totally. Then the third sentence says that Annie knows that Bob does not hold 2 essentially. The fourth sentence says that Bob knows that Annie does not know that Bob holds 2 essentially. So, 2B stands for Bob holds 2, KA 2B stands for Annie knows that Bob holds 2. The negation before that says that Annie does not know that Bob holds 2, and the KB at the leftmost position says that Bob knows that Annie does not know that Bob holds 2 essentially. And finally, this sentence, it says that it is not that Annie does not know that Bob does not hold 2 essentially. So, by now I hope the semantics is clear. This last sentence we can also read as saying that Annie considers it possible that Bob holds 2. When you say that she does not know that Bob does not hold 2, there are 2 negations there. When you combine them, it becomes a possibility relation essentially. It says that Annie considers it possible that he holds 2, because she does not know that he does not hold 2 essentially. And sometimes we represent this with a k hat statement here. So, instead of writing not k a not 2 b, we can write it at k hat a to b essentially, just a short form for that essentially. Here is a situation. So, in this case there are these 3 cards 0, 1 and 2, and Annie picks card 0 and Bob picks card 1 and card 2 is on the table, which is depicted in this situation here, which is in the box. So, these are the different possible worlds, and the real world is depicted with the box with a solid line essentially, which says that Annie has got card 0, Bob has got card 1 and card 2 is on the table, and we will label this state as 0, 1, 2 essentially. So, this other state, for example, here it says that Annie has got 0 and Bob has got 2 and 1 is on the table. Now, you can see that Annie cannot distinguish between these 2 states here clearly, because all Annie knows is that she has got 0. She does not know whether Bob has got 1 or Bob has got 2 and the other card is on the table. So, these 2 states where Bob is 1 and 2 is on the table, or Bob is 2 and 1 is on the table, Annie cannot distinguish. So, that is why we have an edge between these 2 possible worlds that Annie cannot distinguish. So, likewise you can see that even when Annie holds 1, she cannot distinguish whether Bob holds 0 or whether Bob holds 2, and when Annie holds 2 here, she cannot distinguish whether Bob holds 1. And likewise, there are these 3 relations for Bob, as you can see, that when, for example, Bob holds 1, he does not know whether Annie is holding 2 or whether Annie is holding 0 essentially. So, this is the Kripke structure for this situation which is given to us essentially. So, we can make statements like this, that in this structure this formula is true, that Bob does not consider it possible that Annie has card 1 essentially. So, remember that we are talking with respect to this with respect to this given state 0, 1, 2, which is this state here. So, which means that when whatever we talk about Bob, we must talk about in all the worlds which are reachable from that state by Bob. So, the only world reachable by Bob here is this state here from the given state S, and you can see, because there is the only link with label B is to this state, and you can see that in both the possible worlds that Bob considers. In one possible world Annie holds 0, in another possible world Annie holds 2 essentially. Now, this is obvious because Bob knows that he is holding 1. So, Annie cannot be holding 1 essentially. So, but we can look at this formula and say that. Likewise, Annie considers it possible that Bob considers it possible that she has the card 1 essentially. Annie does not know that Bob is holding 1. So, in some sense she considers it possible that Bob thinks that she has got card 1. So, you can sort of go over this formula and try to see why this is true in this given Kripke world essentially. So, we are only talking about the truth value of formulas given a situation and given a world essentially. So, I will take one more example. Here which says that Annie knows that there is a hat, which if you watch carefully over the second K, Annie knows that Bob knows Bob to consider it possible that she has card 0 essentially. So, again you must figure out that why that is the case. So, let us take one more example. Now, this time Kathy also picks a card and she picks 2. So, Annie has got 0, Bob has got 1 and Kathy has got 2. So, again the possible world with the solid outline is a real situation, and we are asking in the context of that what does Annie know and what does Bob know and what does Kathy know. So, really the only thing they know for sure is that Annie knows that she is holding 0, Bob knows that he is holding 1 and Kathy knows that she is holding 2, but they know other things, like for example, this sentence is true. It says that Annie knows that Bob knows that Kathy knows her own card essentially. So, the thing inside the brackets, which is a disjunct of 3 things, simply says that Kathy knows her own card, and if you work through the semantics of this, you will see that this formula is indeed true essentially. It is like constructing a truth table in some sense essentially. And one more sentence, this formula says that Annie has card 0. Now, we know that to evaluate a proposition in a given state, you simply see whether that proposition is true in the given state, and we know that Annie is holding card 0. So, the first part of the conjunction is simple. The second part of the conjunction says, but she considered it possible that Bob considers it possible that Kathy knows that Annie does not have card 0 essentially. So, these are very complex looking sentences, but you can see that we can formalize this whole notion, and the good thing is that if you can formalize this whole thing, then you can ask a machine to tell you whether the sentence is such a sentence is true or not essentially. So far we have only talked about sentences, the syntax and the meaning and the possible world semantics. In the next class we will, without going into too much detail, we will talk about what happens when some actions happen essentially. How when the world is changing, how can you figure out what is happening essentially. That is a subject matter of dynamic epistemic logic. Unfortunately, we do not have too much time and in this course to do that. So, but we will try and get an idea of what kind of reasoning happens there.